Okay, hello. My name is Ingmar Häggström, working at EISCAT in Sweden. I will present the demonstration of the use case IC3, which is VRE support for user-driven analysis. And the people that has been working on this use case is me, myself, and also the people from CNR, Leonardo and Gianpaolo Coro. Yes, so EISCAT is a set of radars up in northern Scandinavia to study the ionosphere and the atmosphere, and higher up, and other processes up in the sky. So the EISCAT is a association consisting of a number of members, countries, and have also affiliate members, which has a shorter commitment period, which is based on the institute level then. So the activities on this use case started 1.5 years ago, and we have selected a couple of algorithms to be shared in this use case, and we have EISCAT is providing two types of algorithms. One is the low-level data display, which is written in MATLAB, but we have now converted it to Octave to be able to run it on the virtual machines that are supported by the G-Cube data analytics platform. Sorry. We have also another algorithm, which is the basic analysis and to produce physical parameters from the data, but which is also written in MATLAB, but that is rather a big package. So it's not easy to convert it to some other system. So, and the output from the runs will be output on the workspace. Also the metadata for the run. So the process that we have selected is the RealTime Graph, which is a MATLAB toolbox, and that produces plots like this. When normally we run it in graphical with a graphical interface on the site, but we can also run it as a batch mode to read recorded data. So it produces a number of plots like this. So first we have the raw data, which is the red data, which is rather complicated set of profiles. And then one can convert these into spectra and for different altitudes and different spectral resolutions and so. And that is so. In this example, we can see there are four different plots that are produced for this run. So the procedure is that we use the storage that we have at the EISCAT headquarters, and we use the data miner, which is running the graphical interface. So the input for the data is the URL to the data that we get from the EISCAT storage, and we in the first version of this we have one parameter to select, and this is the integration time, how much we should integrate the data before displaying a plot. So we stage the input data and at G-Cube, which should be up to about 10 gigabytes of data. Then we run the script and produce the plots, and then these plots are compiled to movies. And then when it's ready, the stage data will be removed because we are not allowed to store so much data there. And the results are emailed. The results are rather modest in size, so it's a reduction of about 1,000 from the input data to the output data. So the GUI looks like this. So I will show the demonstration data of it, how it looks, how it is run. and the output will be a log file and the results, and also an email that you will get. So when you run this, it will produce these data movies then. So here we see an example of a movie. We selected one of the windows that is displayed in this real-time graph. So here we have a number of profiles going from around 20 kilometers of altitude up to 200 kilometers, and we see recorded power from different altitudes. We see also spectra over these altitudes. There is a error. So here is low resolution spectra in kilohertz range. We have higher resolution spectra in hertz range, and also even higher in just a few hertz. Normally, what is run on the radars is the normal analysis is done on the ionospheric echoes, which is we can see here as a line, very thin line over altitudes like this. What we don't produce, which the users has to run themselves, is the atmospheric echoes, which we can see also in this resolution, frequency resolution, which is a rather much more narrow spectra. So we need to resolve it into higher resolutions like this. We see also in this movie, if you look at it, you can see meteors coming in. You see space debris, you see airplanes. So here is a meteor echo. One can see. You could use the airplanes you can see here as moving points. Also the space debris is coming as very big noise squares. Maybe you can go back again so we can see here that was a space debris echo, which is a rather big echo like this, and the airplanes are coming if you want to see them, but they are there sometimes. They are for us, of course, they are not very interesting, but maybe there you saw something in this plot. This is actually a new product for EISCAT. We have not really been doing these kind of movies before, and it's very useful for the users to investigate the data in details like this in an easy way, to see what is really happening. Instead, normally you just have the atmospheric parameters from this plot that is coming. So it is a good tool to find the unexpected echoes or unexpected data from the data. So the next step on this is to work on the data access. Currently, the data is open after 4 years. So if you want to have newer data, we need to work on this. So on some federated ID solution for the data access. It would be good to have to access the virtual the VRE directly from the EISCAT site with a button, which is not done right now. In this case, we are working on this level 2 data, which is the standard archive format, which is a time average the spectral data. You can average over longer times as we saw here. This is a rather advanced format where you need rather complicated metadata to understand it, and also signal processing knowledge, how the data is stored. So we want to develop this data interface further than to produce sets of these semi manufacturers, which are these height profiles and all return spectra like you saw on the movie. and which is then making it much more easy for the users to do their own analysis without downloading a lot of data and reformat it to some sort of more physical set of profiles. So we start with the EISCAT schedule. Looks like this, which is the operation schedule, but we can also select archive. We can also select what data that has been archived. Now we have to go a bit further back in time. So we can go, for example, to March 2013, which I selected here. Select archived and query. Then we get the data that has been recorded, which are these A's. So for the 5th of September, 5th of March, we recorded from 12 to 16 UT about, or 17 UT maybe. An experiment run by Nippon, which is Japan, Norway, and UK, which was the CP1 mode experiment. So then you click on this one, and then you can go to the download page and select download, and then you get this the URL that for the data that you can copy. So now you have the URL in your workspace, and then you go to, I have a link here for this D4Science services, d4science.org. Then you need a user here right now. You can sign in here. It is very easy to get the user. You just ask, and you are allowed. Currently, the running version is under this proto lab right now. So you have to click on the proto lab, and then you go for the data. It takes some time. Analytics. So here you have your environment. So you execute an experiment, which is this algorithm. And now we have there are quite a few of these algorithms. So now we go to ENVRI here. This is the version 2 of this WebTG, which we had here. So here is the input for on these runs. So you can then paste your URL here. That was you got from the schedule page of EISCAT, and then you can select the integration time then here. In the future, in future, there will also be a few more of these input lines. For example, you would then provide your analysis script here, or analysis package that you are accessing on that you are running on one of these outputs from the plots. So normally you will run this first to see which plot you want to analyze, and then you run it again, and then you select which of these plots, which of these windows you want to investigate further with your own tool. So, but right now it is only the movie maker, or so to speak, and then you start the computation like this, and I hope it will run. It will take an hour or so to make this movie, so we cannot wait for that one here, but it is running. It should rather quickly come to 10%, and then I guess it starts to download the data and uncompress it and so. So Control Z. I saved one of this. I was running this for last week, and then after you're running this, you will get a page like this. So your computations complete and so, and then you can download the file. You will also get an email with this. You will not get the files on the email, but you will get the link to this result, which is you can this you have a log file and you have this output file. Then we can also get that file from here. Maybe I don't know, cancel here. Maybe I go to data analytics, and then you can check the computations. So here we were running that run. We were just started. It is 10% completed. You can see here. This one from last week that I was running is here, so I can show that one. So here you have the result. You have the log file of the run. You have the output file, which is the zip files, and you have also the input data stored, and some information used. It was started 24th of August, and it took about 30 minutes actually. Should I could show something more. Yeah, so the maybe I make this big. The log file looks like this. The max the XML file. Oh, sorry. The zip file. It was the text file I should have taken. Or oh, it's not an XML file, but it has the inputs and the output from the actual run. So it is running setting up the virtual machine, running this first to get the data vget of this URL and to download the data, running the Octave script, and this is all the files in this workspace. And then after, when it is ready, you have these movies and T20 AVI, T21 AVI, and T22 AVI in this case. So depending on what experiment you're running, you will get different type of output. So each experiment will have a different mode of output. I can show you how that looked like. Where was it? There was are in this directory. So the here. This is a raw data input, which is rather, which is this complicated way of displaying spectra then. So there are in a number of profiles of different properties of the spectra, like this. So these are then normally what this is the user wants is some output like this, and which is here you have the spectra over from in frequency and of for different altitudes. So you can see it's narrow in the bottom here and getting wider, and then it gets weaker as you go up. Here is the return power. You can see here, maybe this is a low resolution, low altitude resolution data in this case. We have also high resolution data in this T22. It's this is a bit higher resolution and also higher resolution in altitude. So here you see very strong echo at about 200 kilometers, which is caused by we are modifying the ionosphere with a very strong heater, and this runs on for a few minutes and off for a few minutes, and now it's on. You can see with this very strong echo and also very strong backscatter at this altitude. Then it is off, and you get a normal data from the normal ionosphere. Yes, now it is turning on again. So we are running the ionosphere. We are using the ionosphere as a plasma laboratory in this case. So we are modifying the ionosphere, and this is one of a different kind of experiment, but not a natural data then, but more artificial data, but still. Okay, that was the demonstration. Ready.